So far, I have discussed regularization methods that use a penalty term. However, for artificial neural networks, there's a particularly attractive method, a very simple method of regularization that's called early stopping. Early stopping works like this. We just minimize the training error by gradient descent. So this is our error function, and we just minimize it in our usual backprop way. However, every case steps, while we optimize, we plot the error of both data sets and compare the two. So here's the training error. The training error always goes down because we do gradient descent. Every case steps, we also look at the validation error. At the beginning, it also goes down, but at some point it will actually go up again. And then we say, okay, so this was the best performance. This was the minimum validation error. So this is the set of weights that we should use. And this means that during training, you always, every case steps, you already memorize the current weights, but you continue until the end. Then you look at the curve and you go back and you choose as final weights the weights that were here when the validation error was minimal. So this method is particularly easy to implement. We now control the flexibility via the learning time. The idea is that the network exploits the total flexibility only after some lengthy optimization. Basically, we initialize the network with small weights. At the beginning, it's close to a linear transformation, and only during the long training time, the weights grow big enough that the network exploits its flexibility, that the network can implement these very flexible separating surfaces. So if we use weight configurations that arise quite early, the network has not yet exploited its maximal flexibility. So in the end, we'll keep the weights of the minimal validation error, and we have to be careful when we implement this for the following reason. It could very well be that the validation error goes down, then goes up again, before it finally goes down a lot, and then it goes up again. So you cannot just say, well, here it was a minimum, so this is the best validation error. You really have to continue until convergence. Quite often people say, well, now here it looks like it has converged. But no, often if you wait long enough, it will go down again. So you really have to wait for convergence. And then once you have really converged, you can go back to the earlier solution where you found the best performance on the validation set. So I don't really like the term early stopping. Early stopping is a misnomer. It's not an early stopping procedure. It's a going back procedure, going back to the situation where you had a very small validation error. Quite early in the lecture today, I discussed the XOR problem. So here is the noisy version of the XOR problem, where data points are not located in very closely to 1, 0, 1, 1, 0, 1, and 0, 0, but they're really spread out over some region. So on the next slide, you will see 100 data points drawn randomly from these 4 Gaussian distributions. The perfect split for this random data sample in the limit of large number of data points would be a separating surface that cuts out rectangular regions for the positive examples. So now let's have a look at our 100 data points and how backprop in a network with many neurons in the hidden layer finds a solution. So we start here, these are the data points, and we now see how the separating surface moves in, and here is the time counter, and starting about epoch 200, the separation will be very close to the optimal separation. You now see here the squares appearing. Have a look at the data, which looks very noisy, and you see that now the separating surface starts to spread out. So here we get already a worse in the terms of the separating surface. The loss still continues, and now it increases again. The minimum was at 0.144 at around time count of 400. Let's go on and let's focus on this region here. This is sort of the interesting region, and you will see that now the separating surface really goes into this area. So, in summary, if you continue learning for a long time, then the network really develops this very wriggly surface, whereas in the beginning, if you look at the first few epochs, it does much better. And this is exactly what early stopping is doing. Early stopping stops at the moment when the validation error is minimal. So this is the interesting region where the video will evolve to if you wait too long. And we have now just the right moment, epoch 400, where it was minimal, and then it goes up again. 400 to 500, it's minimal, and now it goes up again. So early stopping works because the network at the beginning is not yet flexible enough, but during learning it exploits its flexibility, and you will see now also down here very strange things appearing. So now every data point is fitted individually, and this is what is called overfitting. Okay, so today we have covered a lot of material. I started with the XOR problem. The XOR problem cannot be solved with a single layer, but it can be solved with multiple layers. In fact, multiple hidden layers provide flexibility. We can train a network with multiple hidden layers by the backpropagation algorithm. This is just a smart implementation of the chain rule. It's automatic algorithmic differentiation. It's much better than just numeric differentiation. Well, hidden neurons in a deep network add flexibility, but we have to worry about the problem of generalization. We have to control the flexibility by hyperparameters or alternatively by early stopping, where early stopping means you run until convergence and then you go back to the earlier solution which had the lowest error on the validation base. So we always need to predict well for future data. In the ideal case, you would put aside a test base which plays the role of future data which you never touch, and then you do k-fold cross-validation to find the best configuration. I've covered a lot of material today. All of this is standard material, introductory material, which you find in the textbooks